So we spent the last discussion talking about change of basis, and we already had the matrices sort of cooked up, and we already knew which matrices we needed to use in order to change basis. But of course, usually you have to track down those matrices, and because the Jordan normal form is basically just a fancy change of basis, I think it's important that we at least work through a simple example on given two different bases, how you find the transition matrix that takes you from one basis to the next, right? And so, let's go and consider two different bases for R2. Let's consider the basis 1, 2, paired with 2, 1. And so we'll call that basis 1. And basis 2 will be 1, 2 paired with 1, negative 2. Then we may want to, change basis from one to the other. And basically, what we have to do in order to do that is track down. Suppose that we want to figure out what these basis vectors are relative to basis 1. Okay. Then what we can do is we can say, this basis vector 1, 2 in basis 2 can be thought of as C1 copies of this first basis vector plus C2 copies of this basis vector 2, 1. And, in this case we can already see what these values are going to be, but if we didn't see that already, how could we track down C1 and C2? We notice that this is basically just a linear system, right? This says that 1C1 plus 2C2 has to equal that component 1. And same thing here, 2C1 plus 1C2 has to match this component here. And so we get this little matrix that we'd have to row reduce, right? So we get 1, 2, 2, 1. And 1, 2. And we'd row reduce that, and we'd find C1 has to be 1, and C2 has to be 0. So we won't go through that just yet. Let's consider the second basis vector 1, negative 2. Then same deal, right? We've got 1, negative 2. We can think of it as D1 copies of 1, 2 plus D2 copies of 2, 1. And in that same way, you can set up a matrix that tells you, if you row reduce this matrix, you'll track down D1, D2 that re-express this basis vector in terms of the previous two. And so the matrix that gives that to you is it's basically going to be the same matrix, 1, 2, 2, 1, but with this vector in the column. Okay. Here we had it equal to 1, 2, so 1, 2 went in the column. Here we set that equal to 1, negative 2, so that goes in the column. And so the key feature that you'll notice here is that this is basically the same set of row reduction steps that you're going to need to do in both of these, right? It's the same coefficient matrix. So what we do is we just pair these things together into a single matrix, okay? So we'll take the coefficient matrix 1, 2, 2, 1. We'll take that first column vector 1, 2, and take that second column vector 1, negative 2. And then when we row reduce, these values here will be the C1, C2. These values here will be the D1, D2. Okay? So let's go and work through this. I don't know if you guys have ever heard this joke, but there's a common joke in the math world that says, never row reduce in public. So, the numbers turn out to be a little bit messy here, and so, if I make a mistake, make sure to correct me. But here we go. We're going to, row reduce to track down, reduce this down to the row reduced form. And so we'll take negative 2, row 1, plus row 2 into row 2. So, I'm still laughing. And so row 1 stays the same. Negative 2 of these plus that is 0. Negative 2 of these plus that is negative 3. Negative 2 of these plus that is 0. And negative 2 of these plus that is negative 4. We can then take 2/3 of this take 2/3 of this plus that, and that'll generate a 0 here. Okay? So we'll take 2/3 row 2 plus row 1 and row 1. So 2/3 of this is negative 2. Add that to this, you'd end up getting 0 here. 2/3 of this plus that is 1. And then 2/3 of this plus that ends up giving you, I did this earlier, negative 5/3. And we've got 0, negative 3, 0, negative 4. Okay. So we're pretty close. Just divide row 2 by negative 3. And we get the first row stays the same. 1, negative 5/3, 0, and the second row becomes 1, 0, and 4/3. And there we go. This column is the column C1, C2, and this column is D1, D2. And so that tells us the coefficients that we need to re-express these two basis vectors in terms of those basis vectors for the first basis. Okay, so what we can do then is, given any transformation, we basically use this thing as our change basis matrix, right? And the idea here, it's a little bit backwards from what you might think. The idea is that this change basis matrix is going to change you into basis 1 from basis 2, okay? Because what this does is, if you feed in basis 1, okay? Here's our change of basis matrix, our transition matrix. What we'll do is let's feed in basis vector 1 for the second basis. Okay. Then what you'll notice is that this is basis vector 1 in the second basis. You feed it in here and you end up getting this vector, and this is now expressed in terms of basis 1, right? Because this change of basis matrix said if you take 1 of the first basis vector and 0 of the second basis vector for the first basis, then that's how you can generate B2 in the second basis. So it re-expresses B2 in terms of the first basis. Okay, so this is the expression for the second base, the first vector in the second basis, expressed in terms of the vectors in the first basis. Okay. Same thing here. Suppose that we input the second basis vector for the second basis. Multiplying this out, you'd end up getting negative 5/3, 4/3. Okay. And this is now expressed in terms of the first basis, so that the second basis vector, B2, can be thought of as negative 5/3 copies of the first basis vector for the first basis, and 4/3 copies of the second basis vector for the first basis. Okay, and so a way of changing the basis for a matrix. And so let's go and just consider this matrix here. Where it's pretty much just chosen arbitrarily. Negative 2, 1, 3, 2. Then this matrix is going to be written in terms of the first basis vectors. Okay. And what we can do is we can pre-multiply by the inverse of the transition matrix and post-multiply by that transition matrix. Let me give it a different name. Let's call it P. P for P is going to represent the transition matrix. Okay. And I did the calculation earlier. That transition matrix has the following inverse. So the inverse of that transition matrix is 1 5/4, 0 3/4. Okay, so pre-multiply by the inverse of the transition matrix. Multiply by this matrix here, the actual transformation itself. Post-multiply by the transition matrix that we just now calculated, which was 1 negative 5/3, 0 4/3. Okay. And so just like we were talking about last week, this is going to change this matrix into a new basis, right? So what do? We feed elements in terms of basis 2 into this matrix. It converts them into terms of basis 1, multiplies by this matrix that's expressed relative to basis 1, and then transforms it back into basis 2. And so when you multiply these matrices together, you get the following matrix: 7/4, 7/4, 7/4, 9/4, negative 7/4. And this matrix here then, if this was originally expressed in terms of basis 1, that expresses us in terms of basis 2. And so just because all that change of basis stuff is so important, we've basically last week we talked about the concepts behind change of basis, but we didn't really say how you actually compute them. And so this is the key right here, is you just calculate, given your second basis, how do you express it in terms of the first basis? Using this procedure here, you get what's called that transition matrix that basically takes you from basis 2 back into basis 1. Like I said, it's a little bit backwards from how you think. You express basis 2 in terms of basis 1. And so that transition matrix is the change of basis matrix that you need to rewrite any transformation in terms of another basis. So, the reason it's so important is because Jordan normal form is basically just a very fancy version of changing bases. And so let's go and introduce the Jordan normal form. Finally, this is really exciting. Through a change of basis, every matrix can be put into the following form. J1, J2, J3, all the way down to JK. This is what's called a block diagonal matrix. Each one of these blocks is some n by n matrix. They're all square matrices. And so outside of these blocks, you have zeros. And so it's called block diagonal, meaning it's not exactly diagonal, but it's diagonal in the sense that you've got square matrices running down the diagonal. So this is Jordan normal form. And the structure of these Jordan blocks is very, very specific and very special. So each of those J's is what's called a Jordan block. And the structure of a Jordan block is you're going to have some eigenvalue, lambda, so we'll call this Ji. Lambda I is going to be an eigenvalue for your matrix, for your transformation. And that's going to be running down the diagonal. And above these lambda i's, you're going to have ones. Instead of doing an arbitrary size, let me just do a 3 by 3, just so that you can see a little more clearly without those ellipses in there. So you'll have lambda, you'll have these eigenvalues running down the diagonal. And then above those lambdas, you'll have ones, and the rest are zeros. Okay? And so this Jordan block, what it is it's as close to a diagonal matrix as some matrices can get. You know, in a perfect world, every matrix would be diagonalizable, but you know the reality is that most transformations can't be diagonalized, and you'll see that the Jordan blocks are basically as close as you're going to get to being diagonal without actually being diagonal. And the beauty of this thing is that every single matrix can be put into this form. That's why it's called a normal form, is because any matrix can be put into a Jordan form. And so what it does is it basically boils down all these crazy numbers into an almost diagonal matrix. Okay? And so let's go ahead and take a look at the structure of Jordan blocks. You can have a 1 by 1 Jordan block, and that would just be an eigenvalue. You can have a 2 by 2 Jordan block, and that would be eigenvalues down the diagonal with a 1 in the upper right and a 0 in the lower left. Here's a 3 by 3, and then just I feel like it's worth it because we're going to be really, really digging in deep to this form. I know that you guys can see what's going on already, but let's just do a 4 by 4 Jordan block as well. The eigenvalue running down the diagonal, 1's above it, and 0's everywhere else. So there's a 4 by 4 Jordan block. You've got 4 eigenvalues down the diagonal and 3 1's above that. Okay. So a typical Jordan form is a collection of these block matrices, right? So just a couple simple examples. You might have a matrix whose Jordan form has 2 Jordan blocks, lambda 1, repeated twice, and lambda 2 repeated twice. So that's a very typical type of Jordan normal form that you might see. Another example might be maybe you have a single eigenvalue that's repeated, that just appears once. So that's its own little Jordan block there. And then you could have a 3 by 3 with lambda 2. So there's a second Jordan block. And I mentioned earlier that earlier in the course, anytime you have a diagonal matrix, that's in Jordan form, right? Because if you have a diagonal matrix, what you have is all those eigenvalues just appear as their own little Jordan block. And so diagonal matrices are very, very much in Jordan normal form as well. And so, one thing to keep in mind about the Jordan normal form is that it's not unique on some level, but it is unique on another level. Okay. Jordan normal form is not unique in the sense that the Jordan blocks may appear in different orders. So we may have one Jordan block, 4, 1, 0, 4. And then we may have two other Jordan blocks, 3 and 3. Where anytime you have just a single value like that, that's its own little Jordan block. And then you've got this 2 by 2 Jordan block here. And this thing, maybe you have some permutation of it, then technically, these are going to be different Jordan normal forms here. But what this represents is, it represents the same linear transformation, but with the basis reordered. So it's basically the same linear transformation. It has the same mathematical content, but the basis that you're using here is a different order than the basis that you used here. So what we say is that although there's no quote-unquote unique Jordan normal form, it's unique up to permutation of the Jordan blocks. Each permutation of the Jordan blocks represents just a rearrangement of the basis vectors. In setting up a matrix for a transformation, you have to order the basis. And in choosing a different order for the basis, you get a different matrix, but the matrix still represents the same transformation. It's just the basis vectors are in a different order, right? So that's all that's going on. And now, let's introduce an extremely important property of the Jordan blocks, and we'll call it a day after that. So, an extremely important property of Jordan blocks. And let's consider a 3 by 3 in this case. Let's consider this 3 by 3 Jordan block, 3, 1, 0, 0, 3, 1, 0, 0, 3. That Jordan block, you'll notice we've got the same number, and that's true in any Jordan block, same number down the diagonal, right? What happens if we consider this matrix minus 3 times the identity. So we'll call this J. And so what happens when we consider that Jordan block minus 3 times the identity? We notice that, okay, we've got 3's down the diagonal here, 3's down the diagonal here. So when you subtract those matrices, all you have left is just these 1's that were originally above these eigenvalues 3. So it just leaves you that strip of 1's. And now, let's go and consider powers of this thing. It may seem like we're not really doing it, you may not know exactly where we're headed with this just yet. But let's go ahead and take powers of j minus 3i. J minus 3i squared, we're just going to multiply this thing by itself, right? So this row times this column gives you 0. This row times this column gives you 0. This row times this column gives you 1. And then if you did all those same products, you'd end up getting zeros everywhere else. So we notice that squaring this thing basically took that row of 1's and it bumped it up 1 diagonal position, okay? So what's going to happen if we multiply by another power of j minus 3i? That same thing's actually going to happen, where this diagonal got bumped up 1 diagonal position, and then if you do that one more time, it sort of jumps off out of the matrix, and you get a matrix of zeros, okay? So, and we won't work through the product, but you can just sort of take my word for it. Multiply by 1 more power of j minus 3i, and that row of 1's is going to get bumped 1 more position to give you the 0 matrix. And that property, that when you take a power of a matrix and end up getting the 0 matrix, is what's called nilpotency. J minus 3i is a nilpotent, meaning it's not currently 0, but if you take powers of it, it becomes 0. It's a nilpotent matrix. And so if you take high enough powers, it drops down to 0. This is a really important feature that we're going to use a lot as we proceed. Okay. All right, cool. Yeah.